All right, welcome, ladies and gentlemen, to our study of hyperbolas. This is going to kind of follow along the same lines of our study of parabolas and ellipses. The PowerPoint's basically set up about the same way. So we're going to start off with a couple of definitions and basic statements here. So first of all, the definition of a hyperbola is the set of all points in a plane whose distances from two fixed points have a constant difference. If that kind of sounds familiar, because that's almost the same as the ellipse, where rather than a difference, you have a sum for an ellipse. So a hyperbola is basically, my pen. Hyperbola is basically almost like two parabolas. They're not really parabolas, but they're almost like two parabolas facing two different directions. And in the same fashion of an ellipse, we have two vertices, and we have two focal points, and we have a center. And that's the basics of a hyperbola. So we have these things called transverse axes, or a transverse axis is a single thing. It's the chord, which just means a line segment, lying on the focal axis connecting the two vertices. So going from V1, sorry, my pen decides to mess up here. So going between the two vertices, this distance is 2a, which means the distance from the center to a vertex is a. And also the conjugate axis doesn't really have any big effect on the picture itself. It really has effect on how to graph these particular equations. But the conjugate axis is the other direction. And that would go this direction here, even though we don't actually draw it. And this distance would be 2b. So the distance up would be b, and the distance down would be v. But what that really helps us do is one of the ways that we graph this, actually the biggest way that we graph this, is we find our two vertices, then we find a and b, and the hyperbolas actually have, this is an ugly straight line, they have asymptotes. And the equations of those asymptotes actually rely on what a and b are. And what's kind of nice is what this does is it creates a little box right here. It's really badly done, sorry. And you can use this box to draw your asymptotes. I'll kind of go through that a little bit, probably a little bit better on the whiteboard than anything. So here is the first of two pages for the hyperbola. This particular hyperbola is what you'll notice is this x minus h squared, and underneath it is the a value. And because the x comes first, that means that it is a hyperbola that opens left and right. And there's some things that you need to notice here that's different than the ellipse. The ellipse has a plus sign where a hyperbola has a minus sign. And one of the big things that you should have noticed on that last picture is that, as always, the distance from center to vertex is a, and the distance from center to focal point is c. And that's in both directions. Oops. So it goes for the same for over here, on the right-hand side of this particular hyperbola. And what you'll notice is a, that means a is not always the biggest number. And that's very key for us to understand, because here, a is not the biggest number. A could be the bigger number, but it's not necessary. What A distinguishes is A always goes underneath the first half and B always goes underneath the second half of this equation. What makes you know if it opens left and right is that the fact that the X comes first and the Y comes second, which likewise means if Y comes first, it opens up and down. And so some things you'll notice here is the semi-transverse, so the distance from center to vertex is A. You'll notice that the focal points are basically C units away from H. And you just kind of think about this as since it opens left and right, the focal points have to be left and right from center, so I'm going to change the X value. The same thing goes with the vertex, or vertices. What you do need to notice here is the Pythagorean relation for hyperbolas is different than the Pythagorean relation for ellipses. And that comes to do with the fact that C is now the largest length in this particular type of function. And the last couple of things here is the asymptotes. If it opens left and right, the asymptotes are plus and minus b over a. So that's the slope of your two linear functions. And it goes through the center hk. So x minus h plus k. Or goes through the point hk. Okay, so pay attention here. I'm going to switch to the next page. And again, this is now with a opening up and down hyperbola. So you'll notice that y goes first, which means it opens up and down. And all of the rules still apply. Here's your center. From here to the vertex is A. And from here, I didn't draw it yet, here to the focal point is the value of C. You'll notice the focal points are up and down from the center. Again, the transverse axis is still A. The conjugate axis is still B. The Pythagorean relation is the same as the last page. What you'll notice different here for the asymptotes is the slope is just the reciprocal of what was before. But everything else is still the same. So let's get into a couple examples. So what I want to do here is I want to find the equation of this particular hyperbola. So it says the transverse axis has endpoints of -2, -1, and 8, -1. So what I always do is I always draw what I know. So at -2, -1, and at 8, -1, I have 2 points. So the transverse axis, when they tell you the transverse axis, that means these are my 2 vertices. And since they are left and right from one another, that automatically means I go left and right. And what that now tells me is it tells me I have x minus h squared over a squared minus y minus k squared over b squared equals 1. So now we can kind of try to fill things in. This one doesn't actually require too much. But what we can do is we can say, okay, the transverse axis has endpoints, which means the center has to be halfway between those 2 points. And since the distance between is 10, that tells me that this point is 5 units from 8. So it's at the point 3, -1. And you'll notice that's actually halfway between the 2 points. So that's an x minus 3, and that becomes a y plus 1. That's pretty easy. And there's actually no calculations to do in this particular case because, whoa, what happened? Because the distance from center to vertex is A, and I already know that's 5, so that means this is a 25. And the conjugate axis has length of 8, which means this direction is 8, and half of that is 4. So therefore, b is 4, therefore b squared is 16. And there we have our equation. All right, so that shows that I have a hyperbola, opens left and right, vertex of 3, -1, and tells me how to find my vertices and all that sort of stuff. Sorry about that. What if I was to give you 2 focal points and the transverse axis of length 8? So again, I'm going to go straight to just graphing what I know. 0, 15 is up here. That's a focal point. And 0, -15 is down here. That's a focal point. Which means it's going to open up and down because the shape has to go around the focal points. And what's nice about this one is it tells me the center is now 0, 0 because it's going to be halfway between the 2 focal points. So my center is 0, 0. And since it opens up and down, it's going to be y squared. Well, it could be y minus k, but since k is 0, and it's going to be over a squared minus x squared over b squared equals 1. It tells you the transverse axis has length 8, which tells me that a is 4, half of that. So since a is 4, that means this number gets a 16. Now here comes the calculations. Since a is 4 and c is 15, I need to figure out what b is. Well, I can go and say that c squared equals b squared plus a squared. So therefore, 225, which is c squared, equals 16 plus b squared. And b squared is 209. Now, here's what people usually do. They'll solve for b for no apparent reason. The equation is b squared. So I don't really care what b is. I care what b squared is. And you'll notice that it's just 209. Well, here's what's interesting in one of those places you'll find this. Notice that a is not bigger than b in this case. Okay, so pay close attention to that. B is bigger this time. Oops. All right, so here's another one of those types of problems that people kind of don't necessarily enjoy, but I kind of do. It is one that you have to do completing the square. So let's go ahead and start this. You'll notice first it's 25y squared minus 9x squared, which means it's going to be a y minus x. So we'll just keep it this way. I'm going to look at my y's first, and I'm going to say, okay, I'm going to factor out a 25, and I get y squared minus 2y plus blank. Minus, now here's where you have to really pay attention and focus, because I didn't rearrange this. But I took a 9, or a -9 out of x squared, so I'm left with x squared. And I took a -9 out of -54, so I'm actually left with a plus 6x plus blank. And I'm going to add 281 to both sides. And I'm going to add my plus blank plus blank. And let's go ahead and let's not use green because I don't think green's going to come up very well. Let's use blue. All right, half of 2 is 1, square is 1. Pay attention, you didn't actually add 1, you actually added a 25. Half of 6 is 3, square that, you get 9. And you didn't actually add 9, and you didn't actually add 81. What you'll notice that this is a minus 9 to goes with a plus 9, which means you actually subtracted 81. So you have to actually add a -81 here. So I continue this. I get 25 times y minus 1 squared minus 9 times x plus 3 squared equals, if you added this all up, this becomes 225. Divide by 225, and guess what 9 times 25 is? Here we go. We divide by 225, we get y minus 1 squared all over 9 minus x plus 3 squared all over 25 equals 1. We've verified that it's a hyperbola. We could do a little bit of just looking at this and going, oh, my center is at 1 comma negative, or sorry, negative 3 comma 1. My a value is 3, my b value is 5, which means we could solve for c if we wanted to. All right, so that leads us through those 3 types of equations. The last little thing here is something we discussed a little bit in ellipses, is this idea of eccentricity, basically telling you how fat or skinny something is. And for a hyperbola, eccentricity is c over a. And what you can think about is what would be an inequality for E. And this one's actually pretty straightforward because C, oops, oh, I gave it to you. Because C is always bigger than A, E is always bigger than 1. So for a hyperbola, eccentricity is always bigger than 1 because C is always bigger than A. And one of the things that, one of the studies of eccentricity really comes into play with orbits and the comets following hyperbolic paths. Means basically they're following a hyperbola. And here would be an example of that. We're not going to go through this entire problem, but what we have here is we have a comet following a hyperbolic path about the sun, has a perihelion of 90 gigameters. So that means this is the sun, and along its path, where it is the closest, which is right here, this distance is 90. And that distance, you might understand, is the distance c minus a, because the distance from center to the sun would be c, and the distance from the center to the vertex would be a, so that would be c minus a. And then the line from the comet to the sun is perpendicular to focal axis. The comet is 281.25 gigameters, not gigabytes, which means coming up here where this line would be perpendicular to this line, this has a distance of 281.25. And what you could do from that is you could go back to your little table and you know that the focal width is equal to 2b squared over a. Well, that right there is half of your focal width, which means you could probably end up solving for a and for b and for c using these really 3 basic statements. Okay, like I said, I'm not going to work through this entire problem because I kind of want you guys to do a little bit on your own and really have to think for yourselves. I don't always I try not to force feed you guys everything. All right, so here's your assignment for section 3. I hope you guys learned a lot today, and I will see you guys tomorrow.